Now, we are starting chapter 17, and we are looking at the principle of superposition. The principle of superposition is when two or more waves meet at a point in space. The displacement at that point is the sum of the displacements caused by each wave at that moment in time at that location. So, the disturbance at any point here along the x-axis at time t0 is the sum of the disturbances, in this case, of the two waves. So you can say here at time t0, they're far apart. Here at time t equals 1 second, they are both arriving at the 3 meter point. Okay, and we can see here at 2 seconds, now they're overlapping. There's the disturbance of the wave traveling to the right, disturbance of the wave traveling to the left. Here they superimpose. And then at time t3, you can see there's the one moving that way, the other moving that way. If I take this section, add it to that, that's where that comes from. And then at T4, they've passed through each other. So one of the things you need to remember and understand about waves, that waves can move through each other, unlike particles which can't. Okay? Now, when waves move through each other, they come out on the other side where they've passed through each other as if the other one never existed. Now, if we were to take wave pulses and start them from two ends of a string at the same time, they would meet and pass through each other. Okay? Now, let's think about waves and medium changes. I talked about it a little bit last chapter, but we need to talk about it again. Because what happens when I move from one medium to another for a wave is important into the wave behavior. At a boundary, a medium change, three things can happen. The wave can move into the new medium 100%. The wave can bounce back 100% when it hits that medium change. Or the third option is some of it moves forward and some of it bounces back. Think about looking in a glass window. You can see through the glass window, but you can also see your reflection in the glass window. Okay? That's when you get a split, some going through and some bouncing back. Now, if I were to send a wave pulse, let's say, at a hard wall. So I have this attached firmly, let's say, to a ring here in the wall. If I get 100% bounce back, something really interesting happens. When this wave pulse hits this solid wall, when it bounces back, its reflection is inverted. The reflection is upside down. The amplitude hasn't changed, it's just a downward pulse instead of an upward pulse. So if you think about it, when the pulse hits the wall, the string pulls up on the wall, but the wall pulls down on the string. And that's what causes the inversion of the wave. Now, if our string was tied to a ring that could slide up and down a pole, when we would still get 100% reflection, but it would actually reflect upright. Now, let's talk about when I have two different density mediums. We're looking at a 1D wave here, a wave on a string, okay? At the boundary position, here. I'm moving from something that's got a greater linear density to something that has a lower linear density. Okay? At this boundary, the wave speed increases. Now, it's easier for this string to move than that string to move, so we get a wave moving in the new string with a faster wave speed, and then we get a small reflection. So most of the wave goes forward, but a little of it reflects back. And notice both of them are upright. If the new medium is denser than the original medium, then what we have happen kind of looks like this. We move from faster, lighter weight string into heavier string. The part that moves forward is upright, but it's small, and the part that moves back, the reflection, is smaller than the original wave, and it's inverted. If you have a wave on a string that's being generated by a simple harmonic motion source instead of a wave pulse, then on the string, if we see reflections, we could have two waves meeting. The original disturbance and its reflection, its bounce back, at every point in the wave, between the wave generator and the boundary. And when this happens, you get superposition in that wave. So, if I had a string here, okay, and on this side I had some kind of SHM source. So that's our vibration source. And over here I have it tied to a wall. Okay, we're going to get bounce back from the wall. All right? Now, at first, the wave will travel down here, and when it hits the wall, it'll get reflected. Okay, so that's what's going to happen when I have a simple harmonic motion source on one side and a tied off wall on the other. Now, let's start by saying, okay, what if I wiggle this here in the middle and I start some wave pulses and they go out and they hit and once they hit the walls, they reflect back. So notice this was up coming in, it's down going out, it reflects, it inverts. Okay? We know these two waves are going to add together when they meet in the middle. Now, if the conditions are just right, you could get what's called a standing wave when those two waves meet. A standing wave is a wave pattern that does not move. The crests and troughs stand in place, and there are nodes, points in the medium that don't vibrate, because at all moments in time at those positions, okay, the two waves always add to a zero. So at certain positions, the nodes, the two waves always come together to cancel each other out at every moment in time. At other places, they add up to always give you a maximum at a moment in time, which is called an antinode. So the node is where it's always adding to zero. The antinode is when we're getting the maximums. Okay, now let's look at this picture. At our node positions, here, 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 and here, and of course there, the waves are always adding up to be zero. At our antinode positions, which are here, here, and here, the string here travels up and down and up and down. It moves back and forth between the maximums. So at an antinode, the string is going to move back and forth between the maximums. At a node, it's always going to add up to be 0. Okay? So if we were to have a strobe light and look at it, and I'll set one up for us to look at in lab, it always moves back and forth here from maximum to maximum. Okay? Now, let's think about the spacing here for a second. Let me grab round right here. When we think about this, there's one repeat of the wave pattern. So when I have a repeat of the wave pattern, I have wavelength, lambda. So from one node to the next node is half a lambda. If I were to go an antinode to an antinode, it would be half a lambda. Okay? So the nodes and antinodes are spaced half a wavelength apart. So if I took the distance between node 1 and node 3, I'd have a full lambda. If I looked at just 1 to 2, I'd have half a lambda. At nodes, when they totally cancel each other out, we call it complete destructive interference, where they always add to 0. At antinodes, we always get constructive interference, where they add to give you something bigger than each one individually. Okay? So at times t equals 0, cosine omega t equals 1. Okay? The outer curve is the amplitude. A is a function of position x. So notice that the oscillation amplitude changes with position. So here's where I get maximum amplitude. Here it's a little bit smaller. Here it's a little bit smaller. There it's always 0. Come on, work with me. The distance between, okay, I've already told you that a couple of times. For a standing wave on a string, where we have a reflection from tight off end, you can say the boundary conditions are set so that at the boundary, you will always have a node. You can never have an antinode at the boundary of a standing wave on a string. Okay? So this means there are only certain allowable wavelengths that can create a standing wave on a string of length L. For a string of length L and a tension T, there are only certain allowable wavelengths and certain allowable frequencies. The value of M can be thought of as being linked to the number of antinodes in the standing wave pattern. M is referred to as the mode and is the possible standing wave pattern. So if I have a string of length M, the only wavelengths that I can get will be 2L divided by M, where M can be 1, 2, 3, 4, 5, 6, so on and so forth. So let's say that L is equal to 2 meters. Then if M equals 1, lambda would be 2 times 2 meters over 1, or 4 meters. If M equals 2, lambda would be 2 times 2 over 2, which would be 2 meters.
Where are you? We got trouble.
Hello? Okay, I do not know why the camera decided to turn itself off, but I'll assume that it's happy now and that we can go on. Okay? So if I have an open tube, okay, both ends of the tube are displacement antinodes. So M equals 1, M equals 2, M equals 3. Okay? So I have M equals 2, M equals 3. For a closed tube, we get the same thing. The boundary conditions are the same. We would draw the red and the blue lines opposite each other, but you get the same pattern. So for an open or a closed tube, the way we calculate wavelength and frequency is exactly the same as we would for a wave on a string. The only thing we have to pay attention to here is the velocity of the sound wave is based on what the gas is and what the temperature is, instead of on the tension in the string and the linear density of the string. For an open-closed tube, though, we see something different. One end of the tube is always a displacement node, and the other end is a displacement antinode. Or you could say one end is a compression node, and the other end is a compression antinode. Okay? So in an open-closed tube, okay, displacement here, displacement node, here displacement antinode, node, antinode. So notice here I have a node to an antinode, which is a quarter of a wavelength. Here I have 1/2 of a wavelength and another quarter, so 3/4 of a wavelength. And here I have 1/2, 2/2, and a quarter, 5/4 of a wavelength. So when I have an open-closed tube, I can only have M equals 1, M equals 3, M equals 5, M equals 7. I cannot have modes that are even. Okay? The value of M, the mode has to be different. We see 1, 3, 5, 7, 9, 11 odd numbers. The wavelength is always going to equal 4L over lambda, 4L over M, and the frequency is going to be MV over 4L, or the mode times the fundamental frequency. Okay, so we're going to look at a couple of problems. We're going to look at problems 16 and 19 on page 483 in your textbook. Okay, so we're going to look at problem 16. And then we're going to look at problem 19. So if we look at problem 16, it says the fundamental frequency of an open tube, so F1, the fundamental frequency, is 1500 hertz. And it's open. Okay? And we have a temperature of 0 degrees C, and we have helium. It says, what is the frequency when the tube is filled with 0 degree air? So I want the frequency when I have 0 degree air. Well, this tells us that we're worried about the type of gas and the temperature. So in your book, there's got to be a table of the speed of sound in different materials under different temperatures. Now, I think we have to go back to the last chapter to look that up. Okay. down here. Okay, the speed of sound in air at 0 degrees C is 331 meters per second. And in helium, it's 970 meters per second. Okay? So let's do the problem. Now, we've got an open tube. So we're dealing with these equations. Right? We're told that when m equals 1, the frequency is 1500 hertz. And we know that our speed is 970 meters per second. So 1500 hertz should equal 1 times 970 meters per second divided by 2 times the length of the tube. So I'm going to solve for the length of the tube. So 1500, so L, I'm going to take 970 divided by 2 divided by 1500. I have the length of the tube being 0.323 meters. Okay, now we're talking about in air, where the velocity is 331 meters per second. So the fundamental frequency is going to be 1 times 331 meters per second divided by 2 times the length of the tube, 0.323 meters. So 331 divided by 2 divided by 0.323 says that our fundamental frequency, if it was filled with air, is 512 hertz. So, big difference in the fundamental frequency. This is why when you take a breath of helium and you try talking, you sound really high and squeaky. It's because when you're causing those air vibrate, causing the sound waves in the helium as opposed to air, different frequency. Okay? So let's look at another problem. The next problem I wanted us to look at was problem 19. Okay, if we look at problem 19, problem 19 says, what is the frequency of the light? Looking at the wrong chapter, that would do it. That's it. The problem doesn't sound right. Flipped over to the wrong chapter. Okay, so if I look at problem 19 at the end of chapter 17. It says a bass clarinet can be modeled as a 120 120 centimeter long open closed tube. So L equals 120 centimeters, so that's 1.20 meters. Okay, it's played at room temperature, 20 degrees C, and we're in air. So that means the speed is 343 meters per second. But some of the air inside the clarinet warms up to where the speed of sound is 352 meters per second. Does the fundamental frequency increase or decrease when we go from 343 meters per second to 352 meters per second? And then it says by how much. Okay? All right. So we're looking here at problem 19. Okay, we've got a length of 12 centimeters and we've got a speed of 343 meters per second, and it's an open closed tube. So I'm dealing with the equations that I've got up ahead. And we want to know about the fundamental frequency F sub 1. So F sub 1 here should be M times the speed, M is 1, 343 meters per second, all over 2 times the length, which is 1.20 meters. So 343 divided by 2 divided by 1.20. The fundamental frequency here is 143 hertz. Now, the length stays the same, but the velocity changes. And so this is at higher temperature. So the speed of the sound has changed to 352 meters per second. The length has not changed. So 352 divided by 2 divided by 1.20. The fundamental frequency is now gone to 147 hertz. So the speed went up by 9 meters per second. The frequency went up by 4 hertz. Okay? So by increasing the temperature, we increase the fundamental frequency. Okay, now I'm going to mention beats. Beats occur when 2 sound frequencies are not far apart and they come in and out of phase with each other, causing a distinctive increase and decrease in the loudness of the sound. The frequency of the beat is just the difference in the frequency of the 2 wavelengths. And guys, that's kind of this chapter on the short. I will be adding probably some more to it, but that's where we're going to get to today.